Good afternoon. My name again is Adán Hirales. Today I will be presenting the topic Challenges in Material Discovery, a case study of thermal neutron detection. So our working group is now in its fourth year. Currently, it includes participants from Extreme Materials Laboratory at UCSD and from the Center of Excellence and Innovation at CICESE. In past years, we have had students and researchers from other institutions such as UNAM and the University of Sonora. So why is this problem important? Why does it matter? So thermal neutron detection is a problem where physics is known, very few materials have been tested, and the data is very scarce. Thermal neutron detection is not just about a physics problem, a materials problem, or an AI problem. It is a system problem that exposes the limits of how we currently discover materials. The term system problem refers to challenges where the solution cannot be found by optimizing a single component in isolation. For instance, the physics of a reaction. Instead, the problem lies in the interdependencies and feedback loops between the different layers of technology. What we argue is that even if we discovered a perfect material or develop a perfect algorithm, the detector might still fail to perform poorly because these parts don't work together under real-world constraints. Let me adjust. Okay, yeah, there it is. So an excellent parallel to our description of a system problem is the protein folding problem, AlphaFold 2 and 3. This problem was treated as separate subproblems where biologists focused on evolutionary data, physicists on energy minimization, and computer scientists on pattern matching. Whereas in our problem context, discovery of solid-state material for thermal neutron detection, material scientists focus on discriminating material structure and nuclear properties, chemists and physicists on validating material stability in nuclear reactions, and computer scientists on material representation and discovery. So neutrons throughout matter. Neutrons are electrically charged neutron subatomic particles. This single property makes them fundamentally different from charged radiation. They penetrate matter and interact primarily throughout nuclear processes because they do not respond to electric fields. We cannot guide or detect them in the same way we do with electrons or ions. Instead, neutron detection depends entirely on how neutrons interact with matter, and those interactions change dramatically with the amount of energy that the neutron holds. In literature, you will find that there are at least 4 kinds of neutrons that are the ones that are displayed in this image, which are the fast neutrons, thermal neutrons, cold neutrons, and ultra-cold neutrons. So we are focusing on thermal neutrons because they have a very low probability of producing mutations. This probability is in the order of 10 to the power of minus 10. Thus, they are ideal for the study of matter. Okay, so thermal neutron detection. Neutron detection regards turning a rare nuclear event into a reliable signal. Because neutrons are neutral, elastic scattering alone is usually insufficient to generate a detectable signal. Instead, most of the thermal neutron detectors rely on absorptive reactions that produce charged particles or photons. And those are the reactions that I have highlighted here in red in the table. So this immediately places strong constant on materials, constraints, on materials that we can use. Let me change slides. Oh, let me adjust a bit here. Okay, so thermal neutrons are useful because they interact with matter in ways that are invisible to other probes. By probes, I mean sensors. This single property enables applications across very different domains. I list a few here in this slide. For instance, in healthcare, thermal neutrons are used to target there are applications in target cancer therapies. In science and technology, there are applications in non-destructive characterizations of material structure and composition. Also, neutron imaging and scattering reveal features invisible to X-rays. In the energy sector and transportation sector, so you will find them that they're used in reactor and environmental monitoring. Neutral systems in extreme environments, for instance, in space. So the environment is evaluated prior to the deployment of a technology. And in defense and security, they're used in non-invasive inspection and monitoring. So in all these cases, the challenge is the same: converting a neutral interaction into a reliable signal. Okay, so the following images in this slide illustrate some of the application of thermal neutral detection. So we have examples of some of the ones that I mentioned earlier, neutron imaging. So these are kind of like the equivalent of an X-ray. And for instance, in security inspection or in oil exploration, the image is quite small, but let me see if I can make it a little big. You can characterize the types of soils that are present in an area that has oil, for instance. The letters are small here, but it shows that some layers have soils, other layers will have mud, other layers contain, for instance, the oil, and the final layer contains the water. So also in security inspection, so that you can fine tune the kind of particles by the diffraction that the particles produce to generate images that will show you the kind of content that is within, for instance, an automobile or a container. And in hostile environments, before, for instance, deploying a satellite or a rover into another planet's surface, studies are being conducted so that first the kind of types of particles are analyzed. Why is that important? Because if they can produce bit flips or other kinds of reactions on the hardware that when it is operating in that environment, the system is operating in that environment. Okay, so thermal neutrons are notoriously difficult to detect, and that difficulty is what motivates the search for new kinds of materials. Okay, so how are materials discovered today? Before discussing computational and generative approaches, it is worth asking this simple question: How are materials discovered today? To appreciate why new approaches are needed, let's briefly look at some of the materials, how some of the materials are typically discovered. So the main strategy is sometimes, I wrote it here as trial and error. sometimes you'll find in literature that it's called shake and bake. Yeah, but when you do that approach in laboratories, sometimes you cannot test all the combinations of probable material, probable reactions coming. And because there's trade-offs, so trade-offs in terms of stability, cost, or performance. Uh, Also, the timeline to discover materials, a new material is very long. In our research group, we're not only doing the theoretical work, we are also working on building the materials. So, for instance, for a boron-based detector, which we are developing, um, more or less, it has taken around 5 years now, and that's only one combination. So, yeah. So, in practice, finding new materials in a laboratory setting, it really takes a long time. Okay, so why material discovery is a bottleneck? So high-performance detectors often require scarce elements and complex synthesis routes. This limits both scalability and deployment. Finding new stable materials has traditionally relied on careful experimentation and analysis of a very limited number of candidates, as I've mentioned earlier. And also, the number of possible compounds is astronomically large. That's on the order of 10 to the 100. So finding this in a new material in an exhaustive way is both intractable and economically infeasible. So these constraints force us to ask a different question. How do we search for new materials at all? Let me adjust this a bit. So yeah, so discovering materials using computational methods. So because experimental exploration is slow and expensive, materials discovery increasingly relies on computational search and modeling. So in practice, researchers typically use two complementary strategies, generalized as forward virtual screening and inverse design. So forward virtual screening follows a search first, evaluate later paradigm. It assumes the existence of a large database of known hypothetical materials and filters out candidates based on their predicted properties. So strategies that fall in this class are highly computational intensive. Examples of two of them are elemental substitution used by first principle calculations, and also generic algorithms. So in contrast, inverse design starts by specifying a target property and then ask some magic model that we construct to propose a material structure that satisfies that restraint per se. Okay, so example of strategies are generative models such as the GANs, the conditional variation autoencoders, and lately also diffusion models are being used. Both the diffusion models are used and transformer-based models to discover new materials. Okay, let me change slide and adjust. Okay, so now let me talk about challenges that we have experienced in conducting this kind of research. So this research, in our project, we found that the hardest challenge was really not training the model. It was coming to agreements. on things such as what is relevant? What does relevance mean? So physicists, material scientists, and machine learning researchers often approach the problem from very different perspectives, particularly when it comes to data and methodology. So from a data perspective, physicists and chemists tend to focus on physical properties that drive the desired outcome, such as the material class, the density, and the interaction mechanisms. In contrast, computer scientists focus on representation, information loss during encoding, and model performance. Similarly, when it comes to approach, physicists and chemists emphasize on the underlying physics and chemical processes that lead to the material, while machine learning researchers focus on how materials are represented and how the latent space or the solution space can be interpreted. Ultimately, what a group defines as relevant is a human decision, but our models require that such decisions be translated into numbers. So this is an example of consensus that we had as a group for our case study. Reaching a consensus on problem formulation took around a year and a half. So we had a lot of discussion and argued on topics on topics that regarded what kind of elements of ions were we going to analyze. So we came to a conclusion that it would make sense to analyze those which were abundant. So also selecting abundant elements or isotopes is not enough, because we also have to consider if those isotopes will produce the desired outcome at a the desired outcome. So that was like another decision that allowed us to filter out a lot of the elements in the periodic table. And also, we associated with a well-defined measurable signal. So we also did a lot of research on what if those isotopes were capable of producing the signals that we are expecting to see. So this task in general and defining the problem was not easy. So it took a lot of conversations, and finally we came up with a problem formulation that is the one that is shown here. I will not go into detail on discussing. I'm just trying to point out that in order to come to a consensus, it really takes a lot of work. So another challenge that we had was data scarcity. So if relevance is hard to define, data needed to define it is scarce. And this statement is very true in practice. So in material science, we often have a rich structural data sets, but very limited information about how those materials interact with neutrons. So this imbalance becomes very critical when we try to train or evaluate generative models. In addition, much neutron-related data is inaccessible due to security constraints. So yeah, when it comes to nuclear reactions, there's not much open data. So further biases the model that eventually we want to train. So models cannot learn in general what the community does not share. So this is another example of a discussion that took us quite a long time. So in our case study, we anticipated data scarcity across multiple dimensions. For instance, limited in-domain literature, incomplete ion interaction data, sparse nuclear reaction data, and poorly characterized energy levels. And all of those problems did occur. One of the most significant challenges was the lack of data for something which we call the macroscopic cross-section. While some data sets provide isotopic microscopic cross-sections, to our knowledge, there are no data sets out there for macroscopic cross-sections for obviously new materials. So that is understandable. I mean, something new is not characterized at all, right? So this raised a fundamental question for us, which was, should we model the desired signal ourselves? However, modeling is not, again, straightforward because before computing the macroscopic cross-section, we had to address a key open question. For instance, this key open question was, how can the macroscopic cross-section be accurately computed when ion energy distributions are not normalized across measured range? So yeah, what I'm trying to say is that the data that is out there is usually evaluated separately for different kinds of isotopes. And then when we want to add up all this data, the data is not normalized. And so how can we model something which is not measured equally, and as we need some kind of normalization method to be applied? So that took us also like a year of work to create, to use a model to estimate the response variable that we wanted, and a lot of work on the normalization phase, not even reaching the learning phase. Okay, so another challenge, big challenge, was also material representation. So before any learning can occur, we must decide how matter is represented. And we did a whole lot of literature review, and almost in 3 years of work, we only found three methods of that were among the most sound, per se, that allowed us to represent the characteristic of the structure properties of the materials that we wanted. So key representation choices that we procure were the ones that are listed here, which was scale. So that was one of the first questions that we had. So we ask ourselves, should we model unit cells or lattice or supercells? So should we consider local atomic environments or long-range order? Another criterion was ideal or real materials, because when you see the data that is real data, no material is perfect. So for now, we restricted ourselves to consider only defect-free materials. Eventually, we want to consider materials with defects and disorder. So another criterion that we paid attention to was encoding. So encoding is very important. Questions that we asked was, does the representation support invertibility? Is it robust enough to capture sharp resonances? And secondary neutron interactions was another question. I will explain a little bit on that in a couple of slides. Invertibility to this date is still a big issue because at least the 3 models that we consider the most mature out there can produce new materials, but eventually we need a whole lot of processes to guess characteristics of the newly generated material. So why do we know we need these additional processes? Because the functions that we use to encode are not invertible. So we still in the search for new encoding strategies that allow us that invertibility characteristics. Yeah, so the question here was, what information must be preserved for neutron detection and what can be safely ignored? Okay, let me continue. Yeah, so this is an example of this challenge. So why is it difficult to encode materials in a way that AI models can reliably learn? So what kind of characteristics we want in this encoding strategies? We want the eventual product, which we call fingerprint, is geometric invariant. That is that the representation must remain unchanged under rotation, translation, and permutation of atoms. Also, we want that the lattice space, that let's say the solution space, to be regular. Structurally similar materials should map to nearby points in the representation space, enabling smooth interpolation and generalization. And also, as I mentioned earlier, we want invertibility. So encoding should allow reconstruction of physical, meaningful, and synthesizable structures. So, for instance, these are the current encodings that are out there. And what is basically done, but basically we grab the crystallographic representation of the material, apply radial basis functions or other kinds of functions, and then transform these functions into a three-dimensional representation. But as you can see, you lose information because you have the locations of the atoms, but you would need a model then to try to characterize the size of, let's say, what would be a proper name of the spot, that the yellow spots, so that we can correlate them to the type of atom or isotope that they correspond. Currently, those are the phases that need secondary pre-processing in order to regain the original structure. Okay, so let me change. So this was another challenge, very important one. So in terms of also material representation of highly sensitive signals. So in this case study, the material we consider are composed of multiple isotopes, and their neutron interaction properties depend very strongly on neutron energy. Unlike many machine learning problems where response variables change smoothly, neutron cross-section can vary by orders of magnitude over very small energy intervals, as we can see in this log-log plot. This high sensitivity here is what makes machine learning algorithms generalization process of the signal very difficult to adjust. So a first change is non-uniform energy domains. So microscopic, the images that I'm showing here correspond to microscopic cross-sections, are often reported using different energy ranges, resolutions, and sampling strategies, which makes direct comparisons of learning difficult. A second issue is that the presence of sharp resonances, which are this spikes on the blue signal, Even a small shift in neutron energy can lead to large change in interaction probability. So if a model cannot closely predict those resonance, that is very dangerous. For instance, if we are using this model to react, for instance, to a critical issue in a nuclear reactor, and if the model is not able to adjust to the resonance, then we can have a very serious catastrophe. Finally, we observed also that parasitic and overlapping nuclear reactions where multiple processes contribute to the measured signal are also present. In the current research, we're not considering parasitic signals, and we are only considering both the microscopic cross-section and the macroscopic cross-section. Okay. So balancing physical validity and generative freedom. So this is another issue that we've reviewed in literature. We have not experienced it yet, but I believe that it is also important to mention it. So the community, there's an active discussion on these topics regarding standard generative models can produce physical invalid candidates when physical laws aren't encoded explicitly. That's one open issue. Also, physics-informed generative modeling helps enforce validity and encourages exploration beyond unknown motifs. What this means is that when we encode data, empirical data in the Latin space, the encoding strategy does not tell us the size of the Latin space. So how do we know where we can conduct exploration? So that's an open question. Another observation is that even when models pick up some implicit rules, not all constraints are learned. So additional physics guidance and filtering improves the generation quality. Okay, so let me continue. Okay, so now we've reached the generative models. So in recent years, generative learning techniques have become an important tool for accelerating material discovery. The three major classes of models currently dominate this space that we have observed are generative adversarial networks, conditional variation autoencoders, and diffusion models, which are really based on attention-based models. So these approaches have been very successful in domains such as text, images, and audios, where the structure of data is relatively well defined. However, material science presents a fundamental different challenge. So here, generative models must simultaneously generate across two very different types of information. On one hand, we have features which describe the intrinsic structure of materials, such as composition, unit cell geometry, symmetry, and atomic scale descriptors. On the other hand, we have response variable, which corresponds to physical properties we care about, such as stability, neutron cross-section, or mechanical or electrical behavior. In our case, we are only focusing on cross-section, which is the one that produces a signal. And later on, we're going to focus on stability. So these two aspects cannot be treated independently, and the generative model must learn a shared Latin space where the structural information and physics behavior are jointly encoded. So let me continue. Okay, so this is number 19. Oh, sorry. Okay, so another challenge is the Latin space, itself. So a Latin space, you'll find out there that is kind of defined like a compact representation of high-dimensional data that preserves its essential information. In material science discovery, the Latin space is not just a mathematical compression per se. It must jointly encode both the material structure and the physical behavior. So this raises several open questions that we've been exploring. Well, the first one is, should the Latin space be continuous, discrete, or hybrid? What are the physical meaningful bounds of this space? Again, because we're compressing only empirical data and we don't know how large is the size of the Latin space itself. So another question is how do we define human-centered selection criteria that aligns the scientific intuition and experimental feasibility? So, so in our case, the Latin space becomes like an hypothesis space, and moving in this space is equivalent to finding new materials. Okay, so yeah, so as I've discussed, there are a lot of open questions. So a lot of research opportunities. I list some more here. So at our current stage of research, several open scientific and methodological questions remain. For instance, how do we define in-domain versus out-domain materials? Can language models meaningfully guide material hypothesis? How can we quantify uncertainty and stability in generative outputs? How do we close the material discovery loop from generation to synthesis and validation? So that is very important. And how do we motivate cross-disciplinary creativity and long-term commitment? I think that last question is one of the most difficult ones. So yeah, so as I've mentioned earlier, in our research group, we have, in fact, two research teams. One of our teams is working all of the modeling of the materials and building language model for the selection criterion in the Latin space. Working with encoding strategies and many other things. And there's another team which are in parallel working on the synthesis of the actual probes. I show one of the example here. That is one boron-based probe, and it was out last month. So this is the product of 4 years also of almost 5 years of work. Now for this product, the team is looking for neutron sources so that the material is evaluated. So we need radioactive sources, and I think from our last discussion that those samples are going to be sent to Los Alamos research centers so that they characterize the capability of the material. Yes. So to conclude, the challenge in neutron detector materials is not the discovery. It's not discovering the right model. It's discovering how do we work together. So diverse backgrounds aren't just welcome, they are required. And for those interested in participating in this research effort, please contact me, Adán Hirales Carbajal, or Professor Olivia Grib at UCSD. Thank you very much.
Great. This was a A very interesting talk, Professor Adán. Let's see if there is some question from the participants here at the Zoom meeting. You can open your microphone and ask Professor, or you can write down in the chat. It could be either English or Spanish as well.
Sí, sí, sí.
In the meantime, I have one question. Talking about the thing that you mentioned at the end, no? To have a cultural or multidisciplinary teams. Also, you mentioned it as a first challenge, I think. How do you try to synchronize that multidisciplinary team, or how did you manage the collaboration for this? How was your strategies to reach the agreement between these teams?
Oh, well, it has been a very intensive work. Uh, how have we include people, new people? Well, throughout talks like this. So we always are open and extend the invitations to students, both in physics and chemistry and researchers also in computer science. Uh, Professor Olivia Grieb also has a program which is Enlace, and students are also work in the project throughout that program. Um, and uh, and and we started off working very hard, very hard, because really material synthesis. Well, Dr. Olivia Grieve is very mature in that respect, but in terms of the computation and modeling, well, all of us were just starting. So the work was very intensive, and a lot of reading was done for many years. So in order to do that task, we had weekly meetings, and everyone was had to present something. So, and then we discuss, um, and came to consensus and say, okay, no, this doesn't work. This works, and let's test it and move forward. So basically, that was our strategy.
Okay. Sounds good to get all people collaborating each other, right?
Yeah,
Okay, let's see. Oh, someone raised the hand. It was
Jorge.
Jorge.
Yes. I have a question. I've seen like for material discovery, several kind of algorithms or methodologies like GNNs, and also you talk about the LMMNs, and I've seen also the BLAs. I think that's more for robotic, but what kind of methodology or algorithm do you think it's like a more optimal or has a tendency for material research?
Well, at least from our experience, too. Well, right now with certainty, I can say that the one that we have had more experience with is the conditional variation autoencoders. So GANs work good, but they do not. I don't know. At least we've seen that because the conditional variation of two encoders, in a way, guarantee continuity in the Latin space. That continuity characteristic is the one that allows you to have more certainty on the selection of a new material. So that GANs don't do that. So We are starting to review some works which use attention-based methods, diffusion networks, but we have not tested yet, so I could not discuss if they are good or not.
Thank you. And I have another question, just because I just searched for Hussein. You mentioned at the beginning, and he works in interaction between matter and radiation, right? And then he describes also some part of algorithms in one of his books, I think. He's also working in this area of computation and material research. Yes,
Well,
well, I mean, because I've seen another books like, yeah, I mean, the rigorous books of machine learning, and then another one that
yeah,
joins Python and several numerical methods. But what would be like a good literature to read?
yeah, we only focus on his book on nuclear reactions
Hmm.
because there aren't many methods out there for understanding macroscopic cross sections. So a lot of models for microscopic cross section, but very, very few for macroscopic cross sections. And the one that was, let's say, for now, more digestible and straightforward to implement was the one that Hussein proposed. So that's why we're using his method.
Okay, thank you.
Right. Is there another question from the participants?
Sí, permiso.
Sí.
Gracias a Adán por la presentación, muy, muy interesante, todos los desafíos que se presentan aquí para descubrir nuevos materiales. Yo quería preguntarte un poco acerca de la representatividad, o sea, ¿qué objeto matemático se podría utilizar para representar el universo de moléculas posibles? O sea, ¿hay algo en esa dirección? O sea, un grafo, no sé qué objeto podría ser, o sea, ¿qué nos podrías decir un poco de esa parte?
Sí, de hecho, vaya, ahí sí, sí ha sido un reto fuertísimo porque, como comentaba hace un momento, el problema con la representación que normalmente le llaman fingerprinting, ¿no? Este, es de que hay pérdida de información, ¿sí? Ah, hay estrategias sencillas, desde algo como one-hot encoding. Apenas estoy viendo que algunos están utilizando vectores semánticos, pero están buscando vectores semánticos para creando como una especie de modelo de lenguaje en función de los posibles enlaces entre, entre los, eh, entre los átomos. Eso es muy, muy, muy reciente, pero los métodos clásicos, al menos con los que nosotros empezamos, son basados en funciones radiales. Eh, Funcionan bastante bien, pero al último, pues lo que terminan por construir es una representación equivalente, ¿no? Una imagen tridimensional de la estructura cristalográfica del material, pero luego, al momento que ya se empieza a jugar con el proceso generativo, ok, se tiene una imagen, pero luego se necesita ver cómo estimar las ubicaciones, ¿no? En la nueva imagen, o sea, cómo calcular los centroides en la nueva imagen donde están esas nubes que representan los átomos. Y luego, esas nubes, ah, pues, ¿qué representan, no? ¿Es un hidrógeno? ¿Es boro? ¿Qué es? Entonces se necesitan métodos que después se asocian las características de las nubes con los posibles ah, equivalentes del tipo de átomo. Pero incluso ahí después nos empezamos a preguntar, o sea, esto no es tan directo porque muchas de las funciones radiales utilizan algunas constantes ah, muy viejas de lo que representaría el radio iónico de un átomo, pero no son exactas, ¿no? Y son solamente estimaciones, así que um, ah, son muchos retos. O sea, decir una codificación ahorita que sea muy efectiva, no me atrevería a decir que existe. Ahorita todavía hay esfuerzos por encontrar cómo hacer esas transformaciones, ¿no? Cómo encontrar una muy buena codificación que preserve esas características que mencioné hace un momento.
Gracias, gracias, Adán.
Muy bien. ¿Hay alguna otra participación? Aquí. Doctor, yo sigo como interesado en esos retos como de logística humanas, ¿no? Que luego salen fuera de los proyectos. Y me preguntaba, ¿qué tan retador es el conseguir fondos para este tipo de proyectos?
Pues ahorita estamos buscando. Sí, ahorita todo ha sido por amor al arte, vaya. Que creo que ah, a veces en muchas investigaciones, si nos limitamos a que vamos a hacer algo hasta que estén todas las condiciones, nunca van a estar las condiciones. Sí, las condiciones las vamos creando poco a poco, ¿no? Conforme vamos haciendo madurar los temas, muchas veces pues empezando con nada, ¿sí? Eh, es una labor de consentimiento, digo, de convencimiento, ya que se van viendo claridad y oportunidades, yo pienso que pues las oportunidades van a ir llegando cada vez más. Ahorita lo que nos interesa pues es llegar a resultados que nos permiten ese tipo de gestión y ya después, al menos en la parte experimental, pues ya está ahí más maduro, ¿no? Pero pues, muchísimos años que tiene esa parte del grupo trabajando, pero en la parte algorítmica, pues apenas estamos empezando, ¿no? Y ya estamos buscando algunos fondos ahí para financiar esto, ¿no? Pero creo que, como lo dije, uno no se tiene que limitar a eso, ¿no? O sea, si es algo que te apasiona, lo vas a hacer.
Súper, súper. Muchas gracias. Ahí está. Entonces, pues vamos a agradecer al profesor Adán por su participación en este seminario. Y esta es su constancia de participación que dice sí, el Centro de Investigación Científica y de Educación Superior de Ensenada, Baja California, otorga la presente constancia al doctor Adán Hirales por impartir el seminario Challenges in Material Discovery, Thermal Neutron Detection Case Study. Y firma el doctor Gilberto López Mariscal, quien es el coordinador del programa de Ciencias de la Computación aquí en CICESE. Y pues bueno, profesor, muchas gracias por habernos compartido pues esto tan interesante y pues con la participación aquí de los compañeros. Muchas gracias.
Pues gracias a ustedes y gracias por invitarme.